You could read every single line of a program's source code, compile it yourself on your own machine, and still be completely, silently hacked. And I can prove it. This isn't a theory some paranoid hacker cooked up. It's a real attack, described by one of the most respected computer scientists who ever lived, in a speech that quietly terrified everyone who understood it. The punchline is brutal. There exists a kind of backdoor that lives in no source file anywhere. You can search every line of every program forever and never find it. It is, for all practical purposes, physically invisible. To understand how that's even possible, you need to meet the man who invented it, and the machine that makes all your code actually run. The man is Ken Thompson. If that name doesn't ring a bell, his work does. He co-created Unix, the operating system that basically every modern system descends from. He co-designed the C programming language. Later, he helped build Go at Google. In 1984, Thompson won the Turing Award, the closest thing computing has to a Nobel Prize. And instead of a victory lap, he used his acceptance speech to confess to something unsettling. The talk was called Reflections on Trusting Trust. And it asked one simple, devastating question: how much do you really have to trust the people who wrote the software you didn't write yourself? To follow the trick, you need to understand one thing about code. The code you write is not the code your computer runs. You write in a human-readable language like C. But a processor has no idea what a word like if or while means. It only understands raw binary instructions. So there's a translator in the middle. It's called a compiler. It takes your friendly source code and turns it into the machine code that actually executes. Here's the mind-bending part. A compiler is itself a program. And that program had to be compiled by another compiler. It's translators building translators, all the way down. Now watch what Thompson does with that fact. He builds the attack in 3 moves, and each one is more sinister than the last. Move 1. Imagine you modify the compiler so that whenever it compiles the login program for the operating system, it secretly adds a backdoor. A hidden password that lets you into any account. At this stage it's obvious. Anyone who reads the compiler's source code would see the malicious line sitting right there. Too easy to catch. So Thompson goes further. Move 2. Teach the compiler to recognize when it's compiling itself. When it sees its own source code, it silently reinserts both the login backdoor and this self-infecting instruction into the new compiler it produces. Think about what that means. The compiler now knows how to plant a copy of itself, including all its evil, into any future version of the compiler. Move 3 is the kill shot. Once the infected compiler exists as a finished program, you delete the malicious lines from the source code. You wipe them clean. Now the compiler's source code is perfectly innocent. Spotless. You could publish it, and every reviewer on Earth would sign off on it. But the compiled binary, the actual program that does the translating, still carries the infection. And every time it compiles a fresh copy of the compiler, from that clean, innocent source, it quietly injects the poison right back in. The attack has become self-sustaining. It reproduces through the binary, generation after generation, while the source code stays completely, provably clean. So picture yourself as the victim. You're suspicious. You download the compiler's full source code. You read every line. Nothing. It's clean. You compile it yourself to be safe. And in the act of compiling it, the existing infected compiler on your machine reinfects the new one. The backdoor is now in your fresh build, and it was never in any file you could read. That's the horror. The malicious code exists in no source file, anywhere on the planet. It lives only in the compiled binaries, passed down like an inherited disease, hiding from the very tools you'd use to inspect it. And it doesn't stop at the compiler. The same logic applies to the tool that inspects binaries, the debugger, the operating system, even the chip that runs all of it. Each layer could be lying to you about the layer below. Thompson's conclusion was chillingly simple. You can't trust code that you did not totally create yourself. And no amount of source-level verification will protect you from a threat like this. So is there any defense? Decades later, a researcher named David A. Wheeler proposed one, called diverse double compiling. The idea is to compile the same source with a second, independent compiler, and cross-check the results. If two compilers with totally different ancestries produce a matching binary, it's wildly unlikely they were both infected in the exact same way. It's a clever check. But notice what it still requires. Another compiler you're willing to trust. And that's the real lesson buried in this whole story. Trust in software is never really about reading code. It's a chain, and every link is a person, a tool, a factory, a piece of silicon you have to take on faith. Somewhere down that chain, you always stop verifying and start trusting. Thompson's genius was showing us exactly where the invisible knife could slip in. So the next time someone says the code is open source, so it must be safe, remember the compiler that infected itself and erased the evidence. Open source proves what the code says. It can't always prove what the machine does.